So forget about that. So this would be your palm side of your hand. Okay, so your thumb is pointing to the positive x direction, right? But it is a negative charge, so that the negative charge will have the force going to the left side, right? So this is a force, negative, okay? So that we are going to have the negative charge accumulated on the left side, okay? And then, well, you can also think that is a positive charge, okay? If that is a positive charge, then the positive charge will have the force going to the right direction. Okay, I go with the F positive, so that it will accumulate, the positive charge will accumulate in the right side. Okay, okay. Someone said, okay, anyway, right? I make mistake as well sometimes. That's normal. Okay. So in that case, we should have the right face positive charges, right? So that the right face should have a higher electric potential. Okay, the right side is higher, left side is lower. Okay, so that should be a correct version. Okay. And B, what is the potential difference between the phases of the higher and lower electric potential? Okay, well, in that way, we need to derive and make a calculation, right? Okay, so we have the velocity directly perpendicular to the B field, right? So that would be sine 90 degree. So that we can list the equation for the magnetic force, okay, which is QVB sine theta, sine 90 degree. And when that is a potential difference voltage built, okay, so then there will be electrical field built between the two phases, okay, and assume this electric phase is E, okay, so that we are going to have the QE equals to QVB sine 90 degrees. That was directly QVB, okay. The Q is, we don't need to care about how much Q. I don't need to care about the negative or positive. So we just use the Q absolute value, so that we can have the E equals to VB. Okay. At the same time, the voltage equals to ED, right? And then we can replace the E with the VB, so that it will directly equals to the VBD. Okay, that for all these three parameters, we know it's a number, right? So we can just put the number inside and then make a calculation, which is eventually 3 millivolts. Okay, not sure, someone say 0.320 plus 2. Okay, anyway, if you have question, you can just type the full question. Okay, and the millivolts means millivolts, it just means 10 to minus 3 volts. Okay. Okay. Anyway. Okay. So what we just said, what is the magnetic field's force on the charged particles inside the conduction material? Okay. So how about if we have the charged particle that is freely moving inside space, right? Because if you are saying I have the charged particle moving inside the material, right? In that material, we still have a current flow going into a certain direction, right? In that case, we are just saying, okay, it can generate some Hall effect. It's still not a free moving of the charged particles. So if we have the charged particles moving in the space, especially in the vacuum space, right, it is actually the free moving, right? So what will happen when the charge can free move in the space? Okay, well, we can consider a particle of charge magnitude Q and the mass M moving perpendicularly to the uniform magnetic field B at a velocity at a speed of v. Okay, so we know the magnetic force is always perpendicular to the b. It's always perpendicular to the velocity v. Okay, so that if you have some force that is always perpendicular to your velocity, right, you will make a circular rotation, right? So just like if you have between the Earth and the Moon, right? The Earth and the Moon, you have the gravity force between them, and this force is perpendicular to the Moon's moving direction, and then they will make a rotational. The Moon will make a rotational around the Earth. Okay, so that this force will continuously deflecting the particle, and they are perpendicular to each other, and they will make a circular path, just like what we have here in this picture. Okay, and then the magnetic force, we already know it is QVB. Okay, and we know for the circular force, there is a concentric force required to make the circular force. Okay, and this concentric force is given by the mv square r. Okay, so do you know why it is mv square r? Okay, so it is actually mechanical issue, but I can make a quick derivation. So for example, if you are changing a time of dt, right, you are changing the velocity from this direction to this direction, right? So we assume the changing of the angle is by the d theta. Okay, so that in the vector amount, we have a change of the dv. And this dv, if you assuming it is a very, very small d theta, then it should be v d theta, right? So that the acceleration of the changing rate, okay, that should be the dv dt. That should be v d theta dt. Okay, and then d theta dt is just the angular frequency, right? Angular frequency can also be written as the velocity over the radius. Okay, so in the right hand it would be velocity multiply velocity over the radius. On left side, acceleration is just the force over the mass. Okay, so that we can solve for the force, that we'll have the force equals to mass multiply with the velocity square over the radius. Okay, so that would be the concentric force. It is required to be provided by an internal force. Okay, so that we currently will have the magnetic force to provide the concentric force. Okay, so that it will be QVB equals to mv square over the r. Okay, and now we can actually solve what is the r, because that's actually what we want to take a look. Okay, so we can solve the r, and which equals to mv over the qb. Okay, mv is just the momentum, right? Okay, and we can also estimate how much kinetic energy we will have in such a kind of moving circular particle. So kinetic energy, Ke, equals to mv squared over 2, right? So from the classical mechanics, okay? And then we can replace the v with relationship to the radius, right? So that it will become this one. Okay, so you just put it inside, you have m, right? M square and m get crossed. Okay, so that the above is just the qb r and square. So that's proportional to the r square, right? So what does that mean? That means if you want the charged particle moving in the magnetic field and have very high kinetic energy, you should make it rotation have the larger radius. Okay, that's why we are building the technology called a cyclotron. Cyclo means the rotational, right? Tron means electron, right? This is basically means the rotational electron, okay? And then if we want to rotational have electron has a high energy, why we need them have high energy, right? Because in some state of art study of the physics, you need a high energy of the particles to make enough energy for the reactions between the nuclear atoms. Okay, so for example, if you use the high energy of electrons or other kind of particles to heat other particles, probably they will have generate some new particles, and then we can study all the new particles to understand better about the material, about the fundamental things about the physics. Okay, so that's why we need to build such a huge cyclotron to ensure it has enough energy to do that. Okay, so you can refer to the textbook on the pages 748 for more information. Okay. Okay, and then let's take a look at the period. Okay, the period will be equals to 2 pi r, the circular length, over the velocity. Okay, so the r can be replaced with mv qb over qb, so that it will be this one, right? Because v and v get crossed. That's the period. And then the frequency is just 1 over the period, which is just the reverse. And the angular frequency is 2 pi f. Okay, just would be the qb over the m. Okay, so as you can see, the period t, the frequency f, and the angular frequency omega are all independent of the velocity, right? But that is only valid for the classical mechanics. Okay, if you are going to with a very high speed of the velocity, right, that could be possible. You know, the acceleration of the charged particle in the cyclotron could be achieving like several percent of the c is the speed of light. Okay, in that case, we need to consider the relativistic effect, okay, proposed by the Einstein. Okay, in that case, we should use that. The velocity effect is when it is getting close to the c. Okay, so that the distance calculation should be changed so that we can introduce some term that is related to velocity. Okay, so we need to consider that when the velocity is large enough. Okay, well, why we need to take that to calculation to make sure that it's so accurate. That is because for some experiments we need a synchrotron. That means a synchronized electron. Okay, synchronized means the time phase is the same. Okay, so they need to have everything in the same phase so that we can control the collision between the particles to ensure the reaction is accurate. Okay, someone asked the question, so electron can reach light speed if the radius is big enough. Well, they can never reach the light speed. Theoretically, they can reach the like 99% of the light speed, but they will never go into light speed. Okay, even though it is big enough, because there is a relativistic effect. Okay. Okay, so let's see an example. A uniform circular motion of the charged particle in the magnetic field. Okay, so this figure shows the essential of a mass spectrometer. Okay, do you know mass spectrometer? So this is actually a very common tool to analyze the elements inside the material. Okay, basically what people do is firstly the material should be converted into solutions, right? You can use some acid solution or whatever solution to make it a solution. Okay, and then the elements will become ions inside the solution. Okay, and then you use some way to generate ions. Okay, there are a lot of ways. The sparks can generate ions. The sprayers can generate ions. Many ways. Okay, so that basically they are spraying ions going outside. Okay, and then they utilize voltage to accelerating the ions, right? Of course, it still depends on whether you have the positive ion or negative ion, right? If positive ion, and then you should make it in this way so that positive ion can be accelerated during this process. Okay, if the negative ion, you should probably flip over with the battery, right? Okay. Anyway, it accelerated go into a certain speed velocity and then enter into the B field that is perpendicular to that. Okay, and under this B field, they have some initial velocity. So they will make a circular path, but that's actually only half circular because after half circular, it will hit on the panel, and then there is a detector, and then we can define what is the position between the slit and the heat location, so that we can measure what is the x, and then from the x we can derive what is the r, and we can derive what's the relationship with the velocity, which is also related to the ion's mass and the charge. Okay, so that we can know the information of the mass over the charge. Well, and from that we can derive which element we are having, or which kind of ion we are having. Okay. Okay, someone is asking, that's why a particle accelerator is a circular shape. Yes, that's true. Okay, anyway, as I described, okay, the ions after emission from the source was first accelerated by the voltage and then go into this one, go into the B field. Okay, so the question is, what is the mass m of the individual ions if we already have the ions of charge Q equals to just 1e, okay, 1.6 multiply the 10 to minus 19 coulomb. Okay, so we can do the derivation on what is the relationship between the mass and the x. Okay, so firstly, if we want to know the velocity of the charged particle, we need to know is the kinetic energy change. The kinetic energy change, because we just assume after spraying out from the ion source is just a zero in kinetic energy, but this is actually not true. You know, any kind of ion generator, they have some way to spray it out. When it is sprayed out, then that should have some initial energy, initial velocity. But you know, this initial velocity is relatively small compared with the velocity obtained from the electrical field. So we are just saying, okay, electrical field, the initial velocity is just zero. Then the kinetic energy change would be just the kinetic energy will be obtained. Okay, so that equals to the work done by the electrical field. Okay, and that equals to the change of the potential energy with the minus sign. Okay, so that would be equals to minus Q and minus V. Okay, that's directly QV. Okay, and then we can make the total kinetic energy mv squared over the 2 equals to QV. And so what is for the velocity V, which is the square root of the 2QV over the m. Okay, and we already know in the B field with a certain initial velocity, we have the radius of the cycle equals to mv over the qb. Okay, and now we can replace this v into the square root of 2qv over the m. Okay, and then we put the m and b no, m and the q inside. Okay, m inside is the m square, and then we can make a cross like this. Okay, q inside is the q square. Okay, basically we are just flipping over with the mq. Okay, so eventually we are going to have the 1 over the b and the square root 2mv over the q. Okay, and the x is equals to 2 times of the r. Okay, we can check it back. Yeah, it is a half circle, so that the x distance is actually 2 times r. Okay, sometimes people can make a mistake here. So that it equals to 2 times of this one. And then we solve for this for the m, you will have this equation. So that the m equals to the b square q x square over the 8v. Okay, so we can put in all the numbers, then we can calculate what is the total mass of this ion. Okay, so as you can see, this is a relatively complicated calculation, right? With a lot of units conversion. It has a magnetic units, we have the electrical mu units, and we have the mechanical units, right? So in this case, we should make sure to use the consistent set of units. What we recommended is to use the SI unit, the SI basic units, right? Something like the charge, we only use the coulomb. Okay, the mass is kilogram. Velocity, just use meter per second. B field is Tesla. Electric field is volt per meter or Newton per coulomb. Okay, so by using all of this together, right, you will never make a mistake. Otherwise, you could make something wrong. For example, if you have some problem, say I have mass of several grams, right, or several pounds. In that case, you should transfer it into the SI basic units first, and then make a calculation. That's the most safe way. Okay, of course you can utilize your way, but that's probably not safe. Okay, but if you are careful enough, that's probably fine. We cannot guarantee, right? Okay, here are some applications of the moving particles inside the perpendicular B field. Okay, the first one is the synchrotron. Okay, as we said, they usually build a huge diameter. Okay, well, this is the one in Shanghai. Okay, which has the 420 meters. Actually, in the worldwide, we have a lot of similar ones. Okay, and it is costly, but it is quite useful for the high energy physics studies. Okay, someone probably want to ask, okay, if we just want to accelerate the charged particle to have a high speed, why don't we just use a huge tunnel, right? Then we have the electric field to keeping accelerating the particle, right? So you are saying, oh, okay, I have a huge tunnel, right? Have a huge velocity, a voltage, right? And to accelerate that. Well, theoretically that works, but the thing is there are two problems. Okay, one is you need a huge voltage, right? This huge voltage is not like a kV, something like that. It could be megaV, but that is very dangerous. Okay, as and secondly, you build a huge tunnel, it's very costly. And if we are using this cyclo structure, make the particle keeping cycling, right? So then what we can do is, when it is turning one cycle, we can make a small structure, make an electrical field, and make an acceleration, and then so that they can turn another round, turn another round until it has a relative high energy, right? So this is actually a better way if you are considering the cost, if you consider the safety, right? So the rotational structure would be better. Okay. Okay, someone asking, can we skip the fourth line? Okay, what do you mean by fourth line? Because you will get the formula, basically m equals to b squared. Are you talking about here? Yes, well, not sure. Oh yeah, yeah, you can skip the fourth line. That's fine. Okay, but the fourth, this line is just to introduce the x to replace the I, right? So that's the same, right? Right? But you think it's unnecessary, but the problem only gives the x, right? That's why we use the x inside. Right? But if you firstly calculate what is r and then directly utilize the equation you gave, that is possibly also fine. Okay. Anyway, and okay, so this is one application that is on the synchrotron. And we also have another application that is magnetron. Okay, what is magnetron? Okay, magnetron is just okay, you have the high frequency magnetic field. Okay, and then you can let the electron moving inside the magnetic field, and then it has a oscillating electron moving like this. Okay, and then in that way, because it's a high frequency, we can generate electromagnetic waves propagating outside. Okay, and this is microwave range. Okay, so basically it is just a microwave generator. Okay, and then microwave have some applications. Well, it can use sometimes it can also be used as for the communication, but that's one thing which is more common in our life. That is a microwave oven. Okay, so microwave oven was the microwave was generated from the magnetron, which is initiated initially by the high frequency change of the magnetic field. Okay, this is related to the charged particle moving inside, and then when the microwave was generated and absorbed by the food. In the food there are a lot of different molecules. For example, very common one is the water, water molecules. Okay, water molecules like two hydrogen, one oxygen. Oxygen is a little bit of negative, hydrogen is a little bit positive, right? So that when the EM wave, electromagnetic wave is just like some electrical field and magnetic field that was keep changing, right? So that under the performance of the electrical and magnetic wave, this part you can, if you treat this as charged particles, they are just oscillating by itself. Okay, so oscillating is just the heat up is basically saying is have a higher vibration. Okay, so that it is oscillating. That means the temperature was increased, so that the food can be cooked. Okay, that's another reason why we cannot put metals inside, metal foil inside the microwave. That is because if you have the high frequency microwave, and then the free electrons inside the metal foil will oscillating too fast. Okay, and then they are free. It's not like the other material. Okay, other material they have some limitation, but the inside the metal is free. Okay, then free moving can make us too much heat so that it can be explode or even burned. Okay, your machine. Okay, so that's the function of the microwave oven. Okay, so we just talk about what is the magnetic force on the charged particles, either in the metal material or either in the free space. Okay, but we can also have another force, that is the magnetic force on current carrying wires. Okay, so the magnetic field can have force on the electrons. It can also have the force on electrons moving in the wire, but not only it can make the Hall effect. Okay, on the two sides, one side has a higher potential than another one. It can also have the force on the wire itself. Okay, so for example, here, if you don't have the current going through this wire, then there is no force. Okay, so if you have the force current going through that, we can do some analysis here. Okay, so here we have the current going upward, right? That's equivalent to say if it is electron transfer, then the electron will going downward. Okay, so that we can make some judgment on its force, right? Okay, so that would be right hand rule. The B field is pointing to U, right? Okay, so that your hand would be something like this. Okay, this is your palm side. Okay, so that but it is electron, so that the total force is actually on this way. Okay, so that the current carrying wire will have the deflection into the right direction. Okay, in the reverse way, if we have the current going downward, right, then the electron will go upward, and then it's the same B field, so that the force, the sum will go into right way, right? Okay, we can try. Right, so that the force will actually going left way because it's electron, right? So basically, as you can see, it can also have the force going on the wire, and no matter the charge of the current carrier it is. Okay, well, if you are saying it is a positive charge moving, if you do the analysis, you will basically get the same result. Okay, you can try. Well, we can make a derivation on how much charge, how much forces we will have on the current carrying wires. Okay, so if we consider we have the wire segment of the length L, okay, this segment, and it carries current of the I, okay, placed in a uniform magnetic field coming out of the page, okay, and all the conduction electron in this segment will drift past the plane XX. Okay, here is XX. And at the time, in a time t equals to L over the Vd. Okay, so all the electrons in this section will going past this XX, right? Because if the current going upward, the electron will going downward, right? Okay, so we can firstly estimate how much charge will passing through that plane. Okay, assuming the total amount is Q. Okay, then the total amount Q equals to the current I multiplied with the T. Okay, and the T is the time required for all the conduction electrons drift passing the XX. Okay, so which equals to L over the Vd. Okay, and now we can take the force, calculate how much is the force on the total charge inside this L segment. Okay, which equals to Q Vdb. Okay, so this Q is the total Q inside the L, not just one electron. Okay, and then we can replace this Q into the IL over the Vd right here. Then the Vd and Vd get crossed. Okay, so eventually we have the ILB and sine theta. Okay, of course, here it is just a 90 degree, but it may not be really necessary to be 90 degree. Okay, so in another word, is FB equals to ILB. Okay, so we can see we can check the direction. Okay, so FB's direction should be along the VD cross product of the B, right? Of course, we need to consider whether it is negative or positive. Okay, so we should go with the negative VD multiply with the B, cross product with B. But the B field is the direction is still there. But what's the change is they have the current and L here, right? Then the current L, the direction is actually just the opposite of the velocity of the electron, right? So that if you are saying we have the current L, it will make a vector, right? Well, sometimes people use the current as a vector, and then we multiply with the L. Or sometimes people say it's the current and the L is the direction, but the L direction should be along the current. But they are basically the same, right? Just treat one as the vector, another one as a scalar, but that's the same. Okay, so this direction is actually opposite to the VD, the direction. Okay, so if we are saying the force is along this direction, that's equivalent to say it is along the IL, the direction, cross product with the B direction. Okay, so that if we want to write it in a vector term for this equation, that would be FB equals to IL cross product with B, or sometimes could also be write as the L. Sorry, something clicked wrong. Okay, anyway, come back. Okay, so two ways for writing the vector form. Okay, IL cross product with B, or equals to LI cross product with B. Okay, so that would be the vector form for this equation. Okay, let's see the question. FB pointing, someone's asking FB is pointing to the right is given or by using right hand rule. Okay, so anything, any direction here should be checked with the right hand rule. Okay, so if you are not sure, just check with the right hand rule. Okay. Okay, so here are something more further derivation. We can utilize the force density, the small f. The small f, okay, and which equals to the force multiply force over the volume, and then volume is just the area multiplied with the length. Okay, F over the AL, and then F equals to ILB equals to AL. Okay, and then the L and L get crossed, so that would be IB over the A. Okay, the I over the A is the current density J. Okay, so that this would be equal to the JB. Okay, and in another word, we can rewritten the force density equals to the current density cross product with the B field. Okay, that would be another form of the equation. Okay, so here, if the magnetic field is not perpendicular to the wire, the magnetic force is just given by the IL multiplied with the cross product with the B. Okay, here the L is the length vector, that has the magnitude of the L, but is directed along the Y segment in the direction of the current. Okay. Well, in another way, that is someone I like to write, it is L I cross product with Z. In that way, we don't need to redefine what is the L vector. Okay, either way is fine. Okay, so if the while is not straight, or the field is not uniform, for example, if we have the while something like this, okay, current going this way, and then B field like this way, right? In that way, here we probably will have force like this. And here we have the force like this. Here we have force like this, because the force is always perpendicular to the current, right? And in this way, we can just imagine the wire was broken into small straight segments, right? We can just cut them into many DL. Okay, just like for the line charge, right? We are cutting them to be many dx, and then can treat each one as the as the charge part, as the point charge, right? Okay, so that here we just cut them into many small segments and treat each one as a straight line. Okay, then we can calculate each df. And then the force on the wire as a whole is a vector sum of all the forces on the segments that make it up. Okay, well, but of course, here not only we need to consider there is a total force, we also need to think, right? There is could be some torque, right? Some could be some deformation, okay, because the force distribution is like that, okay. And in the differential limit, we can rewrite as the dFv equals to I and the dl cross product with the B. Okay, of course, sometimes the B is also may not be uniform. So we should probably say the B is depending on the location, right? So that we should find the resultant force on any given segments of the current by integrating the equation over all the arrangement. Okay, so that would be the case when we are treating with when the y is not straight or the field is not uniform cases. Okay, so there is an example here. The magnetic force on a wire carrying current. Okay, so there is a straight horizontal length of the copper wire has a current of the this one, and so that what are the magnitude and the direction of the minimum magnetic field B needed to suspend the wire, which is means to balance the gravitational force on it, right? The linear density of the wire is whatever. Okay, so we have the wire which is pointing to us, right? So we have only a point. That's why I say it's not only for the B field, it can also be used for electrical field or the current. Okay. Okay, anyway, it's already 3:15, so we can make a break, and then I'll come back at 3:30 at the same time. Just feel free to ask questions. Okay, someone is asking how should we do the integration? If it is x direction, for example, we integrate L cosine theta cross product with b. Uh, well, if you ask in general speaking, okay, so we should have the integration over the three-dimensional calculation, right? So basically, you can if you really want to do, you can just say, okay, I have the force along the x direction, y direction, z direction, right? And then integration uh, by each direction, and then you have the total vector as there. Okay, but in general speaking, if you are saying for these forces, basically we will not go to that kind of complicated, right? Basically, we are just say you integrate from one or two direction, okay, adding together, that's probably fine. So you will see some example, and you can see the mathematical part is not that difficult. Um, of course, there could be some integration equation that probably you need to check, but that's it. And for the mathematics, there is a course called multi-variable integration, so that probably can solve such kind of equation. Okay. Okay, so let's continue. Okay, so firstly, for this example, firstly we can make a judgment on what kind of force direction we are going to have. Okay, so we have the current direction pointing to us and B field going to the right side. Okay, then we can use the right hand rule, right? So that would be the magnetic force going upward. Okay, in that case, we can make the upward magnetic force to be in balance with the gravity force. Okay, so magnetic force equals to ILB, L cross product with B. Okay, and then we have the sine theta, but the theta is just 90 degrees, all perpendicular to each other, so that it will be just the ILB, which make it equal to the gravity mg. Okay, so that we can have the final equation, which is B equals to mg over the IL. Okay, m over L is actually the line density. Okay, so that we can be written as m over the L and multiply with g over the L, v over the I, so that would be this put inside the number, and we can calculate what is the B field required to make it floating, suspending on the space. Okay. Not only we can have the force, okay, generated on the current, right? But some case, if you have a current loop, right? The current loop is like, okay, you have the force upward in one side, you have the force upward, downward in the other side, so that you can possibly generate some torque. Okay, so the force exerted on the current carrying conductor. So that conductor is placed in the internal magnetic field. Then this force can produce a torque on the current loop in the magnetic field. Okay, for example, if we have a rectangular loop of wire, something like this, okay, the carrying of current free to rotate about a fixed axis, okay, is rotational this way. So probably you want to ask why the current can rotational in this way. Did we connect it to the battery in the middle, or is that a superconductivity? No, that's not that really. Actually, it is easy. Okay, so if you can make a current something like this, okay, and make this gap really small. So basically, you can treat it as a current loop of the rectangle shape. Okay, so and then we have the magnetic field, we have the magnetic force, which can make the torque. Okay, so firstly, we need to define several things. Okay, firstly, we can think the magnetic field B field generated is horizontally and is uniform. Okay, so that B field is a constant everywhere. Okay, and if it's horizontally, that means the theta, especially the theta on the two sides along the current would be 90 degrees. Okay, so that we can simplify a lot of calculations. Okay, and also another definition is the n vector. Okay, the n vector is defined as perpendicular to the area of the loop, n vector. So it is just like if you still remember the flux, right? Flux, we need to have the B field multiplied with the A vector, the aerial vector over the absolute value of the area. Okay, that would be the n vector. Okay, so that we can check with the two magnetic forces, F and the minus F, which is reverse in direction. But here we want to calculate how much torque was generated on the loop and how to make it turn to rotate along its central axis. Okay, so this is actually the reason we can generate the motor, the rotational motor, right? And the AC current output. AC current output is like okay, you are generating a changing magnetic field, right? So that you can make the loop rotational along the magnetic field. Okay, so that's why we can have the rotational motor. Okay, so let's see, we can do the derivation, how much torque we can generate it here. Okay, so firstly, we don't want to take a look at the three-dimensional way, right? We just want to take a look in a planar way, okay? So if we have the rectangle while loop, this is taking look from the left one is taking look from the top of the loop, okay? So that we have the four forces, right? F1 on the side 1, F2 on the side 2, F3 on side 2, 3, and F4 at side 3, side 4, okay? So let's see which forces can make the torque, okay? So we define the normal vector n, okay, as shown here. And we already said it is a vector over the the total area. Okay, so this is a unit normal vector. Okay, and now if you take a look at from the side, okay, the side 1 is just a dot here, side 3 is dot. Okay, and the inclined line is side 2 in the front or side 4 in the back side. In this case, the n vector is pointing in the blue line here. Okay, and this n vector will have an arbitrary angle theta with the B field. Okay, so this theta will be involved in the calculation. Okay, so let's take a look. What is the magnetic force on the side 2 and side 4? Okay, so let's firstly put the equation. For the side 2 and side 4, apparently the current has a certain angle between the B field. Okay, so you can see it is along this angle, right? So that the angle is like this one. That would be equal to 90 degrees minus theta. Okay, so that equation would be I small b sine 90 degrees minus theta. So that's a cosine theta, and which equals to
Okay, sorry. My computer is out of battery. Just put the charge on. Okay, so just give me a few minutes. Okay, we can actually talk a little bit longer, and mixed with questions. So let me restart the PowerPoint, and we can continue. Sorry about that. At the same time, you can ask questions. Okay. Okay, sorry about that. Okay, so if you take a look at the F2 and F4, so they have the equal amount, and you can check with the point they are. Okay.
So that you know, they are actually in the same point. The force is on the same point, is in the center of the line. Okay, and you can see they are in the opposite direction coming from here. Okay, and they are actually in the same line. Okay, so that we can directly say the F2 and F4 is canceling each other exactly. Okay, so these two will not make any torque. Okay, so then the force of F1 and F3, they also have the common magnitude, right? We can calculate from here, right? This is along the side small a, but you know, this is perpendicular, so that you can just use the IAB, okay? But you can see F1 is along this direction, F3 is along this direction. They can make a torque. Okay, what is the displacement between these two aspects to the center? Okay, so we can make some estimation, right? Make a line, right? So this is this distance. Okay, this distance would be the b multiplied with the sine theta and then over the 2, right? So that we can put inside. Okay, so they can produce a net torque. Okay, we have the IAB multiplied with b over 2 multiplied with the sine theta. That's the torque generated by F1. And F3 is the same, the IAB b over 2 sine theta. Okay, adding together, that would be the IAB b sine theta. Okay, this A multiplied with the B is just the total area, so that we can make the total area equals to AB. And for the n loops, okay, n turns, well, we should also multiply with the n, okay, so that the total torque it will be equals to n times with the IABB sine theta, that would be NIA and multiply with B and multiply with sine theta. Okay, so that you can see the sine theta will be just the angle between the B field and the N. Okay, the N, if you are saying, okay, it is just the vector of the A, right? So that if you make the NIA as a vector, right? This vector you can define it as a right-hand rule of the current, and then use the sums point and position. Okay, of course here drawing, well, I see it's a little bit problem, but anyway, it is perpendicular to the loop. Okay, so that if you make it as a vector, so we can actually rewritten this torque as the torque equals to NIA, a vector cross product with the B. Okay, and as you can see, the NIA are all related to the loop itself, because the B field is external field, right? Okay, so NIA is only for the loop, so that we can actually define the NIA as a special term, which is characteristic by the loop by itself. Okay. Okay, someone is asking question. Left hand is only for positive charge. Not sure what does that mean. Okay, anyway. Okay. so that we can introduce another term called the magnetic dipole moment mu. Okay, the magnetic dipole moment of the mu is given by the NIA. Okay, this is for the amount. N is the number of turns in the coil. I is the current through the coil. A is the area enclosed by each turn of the coil. The direction of the mu is that the normal vector of the plane of the coil. But if you are saying the normal vector, we still have the two directions, right? The up and the down. So that we can actually utilize the right-hand rule to define a mu's direction. Okay, that is, if you use the 4 fingers to grab the coil, okay, in your right hand, and which indicate which is along the direction of the current. Okay, so in this case, that would be right, and then you have a thumb pointing to the mu's direction. Okay, so that would define the magnetic dipole moment mu. Okay, so probably want to say I don't have the 2 poles. Why it is called the dipole? Okay, that is because if you are taking a look at the magnet bus, okay, it have the north pole and have south pole. It has a B field coming outside, and then in that case, if you use several loops with the current inside, it will generate the same effect, just like the bar magnet, right? And this kind of loop is our mu. Okay, it's the dipole, the magnetic dipole. Okay, why it is called the dipole? Well, all right, it's sometimes called the solenoid. Okay, why it is called the dipole is because it can generate like a magnetic 2 poles, the north pole and the south pole. Okay, so it's not like the electricity, it only have the mono, you can have the monopole, but the magnetic dipole is always together, right? So that's why we can utilize this loop to work as the magnetic dipole and with its own magnetic dipole moment. Okay, in another word, if you are saying we have a magnet, it also have its own mu, right? Okay. Okay, so we can see there would be the magnetic dipole interaction inside the magnetic field. Okay, so the torque on the coil due to the magnetic field is equals to tau mu b sine theta, or in the direction it is tau the mu cross product of the b. Okay, which is directly given, already given by here. By here, this is just a mu. Okay. And just in the electric case, just as in the electric case, okay, the magnetic dipole in an external magnetic field has an energy that depends on the dipole's orientation, okay, in the field, okay, which is defined as the energy potential equals to minus mu dot product with the B. Okay, this mu will have the minimum value when the theta equal to 0. That is because you can further written as the mu b cosine theta. Okay, so in that way, if you make a plot, when the angle is 0, it will go to the minus mu b. Okay, and then it will go to 0 and you will go to the positive mu b at the angle at the 180 degree. Okay, so as you can see, this is quite similar to electrical dipole. Okay, if you still remember, electrical dipole moment is given by the P, which is equals to the QD. Okay, and the P is the relationship to the electrical field also can make a torque, and the torque is given by the P cross product with the E. Okay, and they can also have the the potential energy, which is defined as minus PE, right? It is just very similar to each other, okay? So, and from the above equation, the unit of mu is given by the joule per Tesla, okay, or ampere square meter, okay? They are equivalent to each other, okay? And you know, from the derivation we had just have, a magnetic dipole will have its lowest energy at the minus mu b when the dipole moment is lined up with the magnetic field. It will have the highest energy when the mu is directly opposite to the field. Okay, that's why we can have the you know, when you have the magnetic bar NS, it will have the electromagnetic field, right? In that case, if you are using a small magnetic compass needle inside that, right, you will eventually have the compass needle getting along with the magnetic field. Why it is that? Because in that way, the compass needle's potential energy can achieve its lowest energy. Okay, so when the dipole moment is lined up with magnetic field. Okay, that's also why we can use the compass to indicate the north direction when we are doing the sailing on the ocean. Okay. Okay, and then if applied torque rotates the magnetic dipole from an initial rotation theta I to another rotation theta F, then the work done WA is done on the dipole by the applied torque. WA equals to UF minus UI. Okay, so this is just basically just a difference between the two. Okay, here we give some typical magnetic dipole moments. Okay, for the small bar magnets, it's 5 joule per Tesla. The Earth is pretty large. Okay, so 8 multiplied with 10 to 22 joule per Tesla. But you know, because the Earth is too huge, in that case, if you are just okay, just testing how much the B field will be generated, then that would not be too much, because that's too huge, too much radius of the Earth. Okay, proton and electron are relatively weak, but there is still existing a magnetic dipole moment. That's one of the reasons why we can have the so complicated electron structure when we have elements with a large number. Okay. Okay, so we should just stop here, because in the next week, the other professor will start from the section 2.2. Okay, in the remaining time, I have prepared some example question notes. Okay, so that we can take a look at these questions and just like a practice for you to help you to deal with the homework and the final exam. Okay. Just a second, let me switch the slides. Okay, the first question. In the crystal structure, okay, the material is made by the crystal structure with different atoms together or ions together. Okay, so in this case, it's ion type material. Okay, the salt, Celsius, chloride, and we have two kinds of ions. The positive one is calcium ions, which with one electron charge, okay, positive, which forms the 8 corners of the cube as a purple color. And the negative part is the chlorine ion with 1 electron charge is at the cube's center, okay, as shown in this figure. Okay, then the edge length of the cube is given. Okay, the Schulze ions are each deficient by the 1 electron, and the chlorine has 1 excess electron. Okay, so question A: what is the magnitude of the net electrostatic force exerted on the chlorine ion by the 8 Celsius ion at the corner of the cube? Do you know the answer of this one? The first question? It would be very quick. Okay, it's 0, right? That is because if you do the analysis on all the forces given by the positive ions, that would be this one and this one. You can see these two has the opposite direction, the same amount, they cancelled. This one and this one cancelled. This one and this one cancelled. This one and this one cancelled. So it ends up with 0. Okay, so that's very quick, right? If you are saying, okay, I just calculate 1 by 1 and adding them together in the vector form, then that's fine, but that takes a lot of time. Okay, so let's say another one. The B: if one of the calcium ion is missing, the crystal is said to have a defect. Defect is very common in any kind of materials, right? So missing an electron, missing an atom, or adding some atom, okay, or some atoms not following the periodic structure. That's very common, okay. So what is the magnitude of the net electrostatic force exerted on the chlorine ion by 7 remaining Celsius ions? Okay, so how to do that? Well, one traditional way is just we calculate what is the force on the 7 ions and then adding them together by a vector adding. Okay, that's traditional way. But in this case, what we can do is just use we are going to have the force of the 7 ions, and then plus with that emission ions, okay, that if you are seeing the vector adding, that would be the force given by the 8 ions. Okay, the force given by the 8 ions is 0, right? Because we just answered the question A, right? It's 0. Okay, so that if we want to have the force of 7 ions, you can just make it as the minus of the just one ion, one positive ion. Okay, so one positive ion's the force on the negative ion would be just K QQ, okay, over the R square. Okay, so here the Q is electron, right? So that would be just the electron charge. Okay, so K is constant, okay, and R is the distance between the positive and negative ions. Okay, so for this R, you can actually estimate it from the side length. Okay, it has a geometric relationship. Okay, so firstly, we can take out this triangle, right? So if you assume this one is A, okay, A, and then the inclined line is the square root of the A, okay. And then secondly, we can take out another triangle, the green triangle. Green triangle will be something like this. Okay, so that one side is square root of 2a, one side is a, so that the middle is square root of 3a, right? And the distance between the between the negative and positive charge, you know, the negative charge is in the middle, positive charge is in the corner, so that the distance is just the square root of 3 over the 2a. Okay, so that is the r, right? So that we can put all this number into this equation, and then the final solution would be 1.92 multiplied with 10 to minus 9 Newton. Okay, so that would be the total force. Okay, but of course that's a opposite, so that will go to the opposite direction of the defect. Okay. Someone is asking, how could you get the square root of 2 multiplied with 8? Okay, so you should know that that's a three-dimensional geometry relationship. Okay. Okay, second problem. In the figure, the positive charge of Q equals to whatever is spread uniformly along a thin non-conducting rod of the length L. Okay. Well, someone is always asking, okay, I have something uniformly distributed, and then whether it is conducting. Okay. So if you say some charge is uniformly distributed in some object, unless it says it is conducting, then it's not conducting. Because if it is conducting, usually the charge cannot be uniformly distributed, right? That's you know, if it is conducting, the charge will be concentrated in some location of the surface, right? So that won't be uniformly distributed. So usually we say uniformly, that just say it's non-conducting. Okay. And then what are the magnitude and direction of the electrical field produced at the point P, okay, at a distance r from the rod along its perpendicular bisector. Okay, so in the class we already introduced the method we can do, right? That's basically divided into the L into many dl. Okay, then treat each one as a point charge and check with the electrical field. Okay, and then integrate with the electrical field, but consider the direction. Okay, and then we can get the final electrical field. Okay, so here is just the same, right? We can just divide it into many small sectors, and each one is dx. Okay, then we treat it as a point charge. Okay, assume the inclined line is r and the distance is x, right? So that we are going to have electrical field dE pointing to this direction. Okay, so this dE equals to k dx multiplied with the charge density, but this charge density can be estimated by the Q over the L. Okay, okay, and then the small r square, right, and at the r's direction. Okay, but in this case, because it's a symmetric between the left and right, so that we don't need to calculate the east direction along the x-axis, right? They are canceling each other, so that we only consider that one along the y direction. Okay, so that we actually need to calculate the dEy. Okay, dEy can be treated as the dE multiplied with the cosine. If we say this is a theta, And then cosine theta would be the big R over the small r. Okay, so that would be eventually dx QL. Okay, and then small r third time and the big R. Okay, and small r is actually square root of the big R square plus the x square, so that we can directly replace that. Okay, so that we just need to integral the dy, and it would be from the L over 2 minus to just the L over 2, right? That would be the total electrical field. Okay, so the integral process I just well, just ignore, but that would be eventually becoming K, Q, R, and okay, and then we can just put inside all the numbers was given in the problem. Okay, so that the final result was is 8.12 Newton. Okay. Well, if you come back, you can try by yourself to see if you can get the same answer with me. Actually, I have double checked with these answers, so this should be fine. Okay. So let's see another one. Okay, the figure shows a non-conducting rod with a uniformly distributed charge, a positive Q. Okay, the rod forms a half circle with a radius r and produces an electrical field of magnitude of E arc at its center of the curvature P. If the arc is collapsed to a point at distance r from the P, by what factor is the magnitude of the electrical field of the P multiplied? Okay, so we can, this would be actually the uniformly distributed charge on the circular, half circular shape. Okay, so that if you do the analysis, we can actually cut them into many sections. But the question is, do we still need to cut that into many dx, right? So if you're just cutting into many dx, then you should calculate how much charge, and then you should calculate what is the angle on that, right? So this is actually a little bit complicated, right? But from the mathematically, it is also simple. You can just divide it into many d theta, right? So that for each section, the length is just r d theta. Okay, and then from this length of the r d theta, you can estimate how much charge you can have, and then treat everything as a point charge, and check with the electrical field. Okay, and then finally calculate what is the final electrical field made by the half circle. Okay, so as you can see, the electrical field generated at P from different sections is this direction, this direction, this direction, this direction, and then finally it is also along this direction, right? So that what we want to do is just calculate what is the summary of this electric field. Okay, so let's do the solution of this one. We can firstly just assume there is a charge density of the lambda. Okay. Okay. So that if we go with an arbitrary theta, and we make a d theta, and then calculate what is the electric field. In that case, the dE will be equals to K and lambda d theta. Lambda is charge density, okay? And then we should multiply with the radius, and then we have the r square, okay? And the r square and r get cancelled 1, okay? And it is along the theta direction, okay? But here, because we know the n-up electric field is just along the right direction, okay? So we just need to calculate the dEx, right? So that would be the dEx equals to whatever we have multiplied with the cosine theta. So that would be the K lambda r cosine theta d theta. Okay, and now we integral the dEx, and the integral range is from the minus pi over 2 and pi over 2. So why it is that? It's because if you take a look at the theta here, right? So this theta, if you want to give it a range, it should be coming from here, which is minus pi over 2, to here, which is pi over 2. Okay, and then after integration, that would be just the cosine theta d theta integration, and the other things are just constant. Okay, K lambda r sine theta and pi over 2 and minus pi over 2. Right? So eventually it will become K lambda over the R, right? And also you can check the lambda multiply with the length. The length is actually half circular length, so that's a pi r. Equals to the Q, right? So that the lambda is just Q over the pi r. Okay, so that the total answer here would be multiplied with the K, then multiply over the R, like this. Okay. Then if you compare with the electrical field here, so which can be directly calculated from the point charge, that would be K Q R square. Okay, so you can check with this ratio. There is some problem here. Oh, here there is an additional 2 times here. Okay, because the integration can make a 2. Okay, so that's 2 times. Okay, and then you can make the ratio. Then the final ratio is pi over 2, which is about 1.57. Okay, so that would be the factor of the magnitude of electric field multiplied. Okay, someone is asking, okay, is that lambda is Q over the pi r? Yeah, yes, that's correct. And secondly, can we integrate from 0 to pi? Well, that actually depends on how you define from the theta, right? So in general speaking, you can integrate from the theta to pi as long as you are define the theta as this angle, right? If you define in this angle, it's probably not a cosine theta, right? So it's probably you should multiply with the, I think it should be with the sine theta. And then after integration will be cosine theta, then integral from 0 to pi. That's still that would be still 2 after integration. So you will give the same result, right? So the question is still, right, how could you define from the theta? Okay, so we already have passed a few minutes after 15, but we missed a few minutes, so that's fine. So we can finish today, and then we can continue talk about these problems in the next lecture on the Thursday. Okay, so let's see if you have question. As things getting easier, 0 is included. Okay, anyway, it's fine, I think. Okay, someone say, how could we get pi over 2? Oh, that is related because we are defining the theta in this way, right? So you can consider this position as this theta equals to minus pi over 2. And this position is pi over 2, right? So that's integration from minus pi over 2 to pi over 2. Okay, any other questions? Oh, constant k. Okay, constant k is just k equals to 1 over the 4 pi epsilon 0, right? So I talked in the beginning, it is the Coulomb's charge. Okay, so that equals to 9 multiplied with 9. Okay, 10 to 9. Okay. Okay. So we just think of the half circle as a unit circle in the graph. Not sure what you are talking about. Okay. Someone says they canceled. I think on this Thursday it's not canceled. The next Thursday was canceled. Okay. So be sure to enter this Thursday. Okay. This Thursday is still February 4th. It's not canceled. Next Thursday is canceled. Okay. The answer for the left electrical field, final electrical field is 2kq over the pi r square, right? But if you are asking what factor the magnitude, you have the electrical field at the p point, that would be pi over 2, which is 1.57 times. Okay. So this is, if you are saying, this is E1, this is E2, right? And the ratio is E1 over E2. Okay. Yeah, because they are asking by what factor. Okay. Okay, thank you. Okay, sorry about the chat issue. I got it won't happen again, okay? And if you don't have questions, then we can finish and see you on Thursday. Bye-bye.